रिकॉर्डिंग उसमें भी रेकॉर्ड होगा इनोवेशन हुआ क्या चेक किया
Shall we wait for more people to come?
No, you can start.
I can start. Thank you. Okay. So, good morning, everyone, and once again, thank you for being here with these 5 days of course, which I hope will be useful for you. As I said, I would like my lectures to be as interactive as possible. So I encourage you to raise your hand, interrupt me, ask questions, and express your views. Okay, so it's perfectly okay. Don't feel shy. I really want to make this chance an opportunity to raise new ideas and to possibly also start new cooperations. So I decided to start with a short introduction about my background and my context so that in view of possible, first of all, to give you a sense of where my lectures come from. So why I gave a certain perspective on the topic rather than another one. And then also to see what lies around me in my home institution, so that we can, so that you can see what opportunities may be there to collaborate. So I will briefly present the context, also the courses that are out there, and a couple of research topics, and then some concluding remarks. So the University of Pavia is one of the oldest in Europe. Some very old documents may date back to 1200 years ago, when a first nucleus of the university was started basically at the time of Charlemagne. But anyway, apart from that, it's a long tradition. So we are a small city with a comparatively big university. So we have a network of services, including residential services. So one of our strong points is that we can really build a community of students. Okay, not just teaching activity, but also something which is really related with student life. And we have approximately 26,000 students growing. I'm not talking just about technical topics. It's a so-called generalist university. So we have several different topics. Engineering, which is where I am from, is about 6,000 students. Okay, so a large part of the university, but still not all of the university. And about 10% of these students are from abroad. So now zooming into my school, it's the engineering school, which is much more recent, way more recent than the university itself. We are the youngest brother. Okay, so sometimes we are looked from up down by the other faculties, but we're still fine. Many courses are taught in Italian, but we also have 5 graduate courses in English, where many of the foreign students end up. In the engineering school, we have 2 departments. One is, as you see here, the electrical, computer, and biomedical engineering, which basically groups all of the IT topics in one department, and that's where I am from. So if we further zoom into this department, we find our research group, which is the telecommunication and remote sensing group, based on the same name laboratory, which also includes a teaching laboratory. So we have a research lab, and we also have a teaching lab where we teach students, especially with the hands-on activities. Our teaching activity are shared across the electronic engineering and computer engineering graduate courses. Okay, so the content of the courses is generally suitable for those two backgrounds, which means that we have a part of the teaching which is on how the hardware of remote sensing devices works, which is especially focused for electronic engineering students, and much of data processing, which is suitable for both courses, but it is especially interesting to computer engineering courses. So we look at both aspects of remote sensing. The subject of this course is remote sensing. When we think about remote sensing, we see both sides of the devices and the data processing. Okay? And okay, I think I can skip this. And if I move to the research areas of our lab, I could classify them into, well, basically two main topics: urban remote sensing and agricultural remote sensing. These research activities are mainly conducted by my colleague, Professor Paolo Gamba, who is very well known in the field of remote sensing. He's also been the general chair of the Geoscience and Remote Sensing Society. And I work mainly on agricultural remote sensing, hence the last lecture of this course. Both threads share some research activity with risk. So we do not do research on risk and risk modeling. Okay, that's not our job. But we have an eye in both research threads. We have an eye on providing information which is relevant to risk computation. Okay, so like for example, providing information to insurance companies which may be interested in knowing how many buildings are at stake in a certain area, or what loss can be caused by a certain weather event, extreme weather event, etc., etc. Just to give you a couple of examples. Okay, so this is not our focus, but we pour information into this research topic. Okay, so talking about urban remote sensing, just a few words. When we talk about urban remote sensing, we talk about mainly mapping urban growth, for example, urban growth and urban change. So to what extent and where cities are growing. And this is what we do at a large scale, but when you move to a smaller scale, we use, for example, we identify features for individual buildings using especially artificial intelligence approach or deep learning approaches. I give this example here where we used an AI or a deep learning network to identify typical features of a building like windows or light, signs, etc. These are useful for risk assessment because, for example, the signs indicate the type of economic activity which takes place in a certain building, and so it gives you a clue about how much that building or how much the disruption of the functioning of that building may cost to an insurance company. Okay. Again, these are just examples. If we talk about agriculture and remote sensing, we have various topics that we will see later in the course. And in this field, we mainly focus not on precision agriculture. Okay, precision agriculture is interesting and it's very, very useful to increase productivity, to make agricultural production more efficient. But scientifically speaking, it's not exactly the cutting edge of research. Okay. What we're trying, whatever new we're trying to do here is slightly different, and it focuses mostly on characterizing what happens to crop along the agricultural season. So what types of operations are carried out in the agricultural field at scale, so on a large scale, especially for purposes of inventorying, of highlighting agricultural trends without having to ask every single farmer what is going on with their field, especially in terms of, for example, certification of crops. So independently of whatever a farmer may have been declaring, what is the reality of what happened to that crop. And I'm thinking about organic certification, for example, but not all. Okay, so these are just two quick examples of what happens in our lab and what is the context I am coming from. Coming to the course, this is the programming. Generally speaking, we will have theoretical lectures in the morning and some more practical sessions in the afternoon. In the afternoon, it's not going to be all hands-on exercises. Mostly, I will show you some more practical applications. If you want, I will give you suggestions for doing the exercises yourself. It's not going to take place, well, not much of it is going to take place in real time. Mostly it will be showing you how to do that, and then you can do that yourself. But a part of the theory will also be taught in the afternoon, because it's very difficult to press everything in the morning. So in the afternoon, probably the earliest part will still be some theoretical knowledge passed to you before starting the actual practical session. Okay, I hope we can withstand that, but I trust so. Okay, so what else? Yeah, so some final remarks. I did this brief introduction just to make you know a little bit better who is teaching to you and where the lectures come from. So teaching remote sensing, in my view, or my approach to teaching remote sensing comes from an engineering background. Okay, so I'm not an environmental scientist, I'm not an agronomist, nothing of that. I would like to have that knowledge, but I need to make choices, obviously. I have an engineering background, so I teach remote sensing with the engineering eye. Okay, and you will probably realize that along the course. But please feel free to bring your own perspective into the lecture if you feel there's a need to. Okay. Then we do I do research on remote sensing of vegetation for agricultural and environmental applications. So I'm especially interested in research cooperation in that field, but not only. Okay, and I'm looking forward to further collaboration if any of you is interested. We are also discussing about setting up student exchanges programming, so it may be interesting for you in this respect. Okay, so let me thank again Professor Gupta and his colleagues for inviting me. Thank you for attending this course. I hope I translated it right. And yeah, I encourage you to maybe get in touch via email, but regarding email, please be aware that I receive really many emails. So don't expect quick reply times, because I really can't. But I will try and get you feedback to every one of you. And especially I encourage you to follow me or to collect on LinkedIn to get a better idea of my activities. Okay. And You can also scan the QR code, which will lead you to my homepage on LinkedIn. Okay, so that's all concerning. Oh, sorry, you may still be making notes, so I will leave it there for a couple of seconds more. Questions so far? Yes?
One thing is written multi-sensor data processing. So when we say multi-sensor data processing, so each and every satellite is having different specification.
Yes.
So how will we combine it together for the processing? Scaling down, scaling up, what method?
When I say multi-sensor processing, I mean mostly we have to do with satellites carrying different types of instruments, but especially different categories of instruments. Namely, we can have multispectral sensors, we can have microwave sensors, and generally there's a specialization of research on either multispectral data or microwave-based data, because naturally each of these fields is challenging. So extracting information from one type of data from the other type of data requires a specific knowledge about that. And so that's one side of the problem. The other side is, but yes, that's true, but if you can combine these two types of data, you can get much more information, because you can source some types of information from some sensors and some other types from other types of data. And if you can merge them together, then you can get a larger amount of information about the same object. When I talk about multi-sensor, this is mostly what I mean. This obviously comes with a lot of challenges, because you have, variability even without the same field. So like when you talk about multispectral sensors, there are several different types of multispectral sensors. And so you have to more or less know what type of features you're searching for to determine the exact type of data that you may be interested in. And it's a complex problem, because each type of data has its own limitations and its own features. So when I say multispectral data merging, I mean being able to make your selection, to weigh the pros and cons of each type of data and find the best combination. There's no way of summarizing that in one single procedure or one single approach to the problem of merging the data together. It's mostly a problem of systematizing your requirements and looking at the various types of data that are offered and see what pairing of data may work best for you. Okay. I know, the more specific answers can only be given for a specific problem. So if your question is, how can I face the problem of data fusion in general, there's no definite response. It depends on the problem at hand. Because I agree with you that there are so many different sources of data with so many different features that it's very difficult to come up with a general approach that works for everything. But what I do generally in my lectures is to highlight the features of each type of data. So what can you expect from this, what you can expect from that, so that people can then look at these features and say, okay, this is probably the best combination. Then it may still not work, obviously, but at least you have the best odds of getting what you need. Okay. Any other question? Yes. Yeah.
Is it possible
for the
Contact the teachers.
yeah.
आवाज़ बहुत कम है नहीं मैम फिर वो कूंगा करने लगेगा
Yes.
no we cannot increase
Yes.
it is already to the limit we cannot increase the gain, ma'am. We are increasing everything we cannot only increase one gain
Mhm. Mm. Okay, thank you for the questions. I hope I can answer both of them. So when the first question is, please correct me if I am wrong, how do I do practically, how do I do fusion of different types of data? And the second question is, can I fuse C-band and L-band radar data? I think it's radar data, not passive microwave, right? You're talking about radar microwave. Okay. So regarding the first question, how do I fuse data from different types? What are the approaches that I can use to data fusion when I'm really looking at data? Well, there are various ways. One thing you should do, first of all, to frame the problem is that you're not talking about data in general. I mean, it's not generic data, it's remotely sensitive data. So it's data that comes with time, stamp attached, and with space, location attached. Okay, so obviously, first of all, we need to be talking about the same area, which is not always obvious because, as you may know, each satellite has its own footprint, has its own shape and resolution for the footprint. So you first need to make sure that the observed area is well covered. And that's the first requirement. Then you're talking about data which is acquired in time, and that's another big problem. Because if you think of satellite data, which is what we will mostly focus on, satellite data is not acquired when you want it to be acquired. It is acquired when it is acquired. Okay, so that's one first big problem in data fusion. You don't simply put together data acquired exactly at the same moment from one spectrum of data. It may be multi-spectrum data acquired one day and then radar data acquired the next day or 2 days from that, etc., etc. So the first big issue is, even before adding the features, is how do I make them match temporally? And very frequently you simply can't. Okay, so one possible approach is that to say, okay, let me ignore the time displacement between data A and data B. I assume they are acquired in the same moment and I pile up the features. That's one possibility. And obviously,
During time, I can take some time interval and make a file.
yes, but that depends on the time scale of the phenomenon.
Time display.
Yeah. So because it's something that is changing fast, it's not recommended to pile up multiple features. So generally, especially in agriculture, where things can change fast on the field, it's generally not recommended to pile up too many data from different applications before you move on to the next steps of processing. So the first possible approach is to say, okay, I just take the two nearest positions in time and I combine the features and I use this as a data item to be processed with the others. And then from that point on, I may have the temporary The other possible approach is since you have a time axis involved, the other thing is you can stay in each domain, like for example, you can stay in the optical domain or stay in the microwave domain and look at the temporal trend and try to interpret that trend in such a way that you can take the matching interpretations. Okay? So the possible approach, when I'm talking about low level, okay, when I say features, I'm meaning features that are extracted from the data, not more complicated features. Talking about, okay, I have the data, and I do some slight processing to get to the features that I'm interested in. So this second approach basically means I sit in either domain, I work in that domain on the temporal scale, I find the trend, and then when I do the same for the other domain, so that I have two time series, two estimations, continuous time series, and then I can come to them to have temporally matching features. That's another possible approach. The other possible approach is to use fusion at the feature level, which means that you extract features at a higher level, combining the two types of data. There are algorithms that are designed for doing that. It's all called advantages. There are also disadvantages. One is because of the functionality, which is inherent in using so much data at once. And then there are also, obviously, if you have sufficient amount of data, then you can try to move on to machine learning or deep learning approaches. But that's the next story. That was the first question. The second question was about can we merge L-band and C-band data? In principle, you can, depends on what you want to do. I mean, what is the goal of your
Yeah. See, the frequency band is different for C band and L band. But a few of the, for example, my application is to detect the soil moisture. And the image is acquired by L band as well as C band. Few of the features are very much important, which is extracting from L band. The features are very much beneficial for C band. So, but somehow I can predict that at the time of accuracy point of view or performance point of view. I can't 100% tell that even though the accuracy is more or performance parameter is quite prominent. But I'm not sure about exactly what happened when I'm doing the hybrid data set.
Okay, I think this is quite complex.
Yeah.
So I do need to offline discussion because it takes some time to, first of all, to really understand what you're doing with this data, and then we can maybe hopefully I can help you with it. Okay, so thanks again, and let's move on to the next presentation. So one thing I always tell them is quick revision of the basics of the discipline, because one thing I find very important real one is good thorough understanding of what the numbers you're crunching when you process unique sensitive data really mean in the physical world. Okay, so it's all done. This is something that I really feel when I'm when I'm discussing with computer engineering students. Okay, they obviously are passionate with algorithms, with numbers, with computational efficiency, with data. But sometimes I feel they don't have a real perception of what these numbers really mean. Okay, so they may get nice results, but it's best to really be aware of what happens out there. So this is why I always start my courses with a quick revision of these concepts about electromagnetic radiation. By the way, just let me, talking about this, I would like to know more about your backgrounds. How many of you have basic knowledge of remote sensing, basic or advanced knowledge of remote sensing, and who else is quite new to this discipline? So who has knowledge about remote sensing? Because yeah, I suspected that. Okay. So the others are pretty new to this matter. Okay. You probably have heard about satellite remote sensing or other forms of remote sensing of Earth observation, but you never really got into the matter. Okay. So one basic concept in remote sensing is electromagnetic radiation. Why? Because when we talk about remote sensing, naturally, as the definition, as the word says, remote sensing says it's sensing something from a remote location. Okay, so if you're sensing something from far away, it means that you're transporting information from one place to another, from the observed to the observer. Who can do the job for you? It's electromagnetic radiation, which usually does the job. Why? Because it has two very nice features. One is the fact that it doesn't need any physical support. You don't have to connect a wire between the satellite and the observed area to transport the information. It's wireless, if I could say so, and it's the fastest possible propagation of information. So whatever happens down on the Earth takes only a few milliseconds, even less than milliseconds, to get to the satellite. Okay. So naturally, we go for electromagnetic radiation to do the job. And this scheme is a bit old. You can tell it from how the computing system is represented, but I still use it because I think it's still significant. It's very interesting because it summarizes what remote sensing is about. Remote sensing is about, remote sensing for Earth observation is about having something to observe on the Earth's surface and having a physical system, part of which is provided by nature itself, which acquires information in the form of data and then squeezes information out from this data to get to the user, to deliver this information to the users, okay? For a very broad range of possible application. Yield estimation, urban mapping, disaster mapping, resource monitoring, whatever, okay? Even looking in the backyard of your neighbor, whatever. Security, name one, it's there, okay? So it's a very general scheme, but the interesting part for us is, okay, who does the job in the physical world? It's the electromagnetic radiation. The basic concept of remote sensing is I have something which in the case of multispectral data is generally the sun, which provides to me a wealth of radiation for free. This radiation goes to the observed area, and that radiation which goes to the observed area is the same for all, okay, at least in the area that I am observing. It's the same for all, but then when it lands on the Earth's surface, it interacts with the objects that are located there on the Earth's surface, and part of it is reflected, but the part that is reflected is determined by whatever object was encountered by the incoming radiation. And that's a key concept to remote sensing. Whatever radiation leaves the observed object has been changed with respect to the incoming radiation by the very nature of the object itself. Okay? So if I can intercept that radiation, I can somehow read the message which is contained in that radiation, a message that was collected by interacting with the object. It is through this interaction that the reflected radiation collects the information, collects a message which can be either lost if no one collects it, or it can be read and understood if I place a technical device that intercepts the radiation, measures it, and provides me a raw data set from which I can understand my variable of interest. Soil humidity, for example, or spectral reflectance, or ultimately health status of vegetation, whatever I'm interested in. But the basic point is here. There's an interaction, and that's physics. It's not technology, okay? It's physics. Where I put the technology is here, where I read the message and I pass on the data to the further stages of processing.
ये मिल गया कौन सा
Yes.
11 कितने लाए कुछ बैटरीज भी लाया है
There are various options, each one with its own advantage and disadvantage. I generally talk about satellites, we're serving satellites, which are mostly found between, let's say, 450 and 1,000 kilometers of weight. Okay. So, technically speaking, they're far out of the atmosphere. We don't want to stay in the atmosphere for various reasons. So, the satellites do their job at these heights. You can do remote sensing even in the atmosphere. So nowadays, it's very common to use UAVs, for example, drones, to do remote sensing. But that's, I mean, many principles are shared. This idea is for sure shared. This is a basic concept which is shared across all the domains of remote sensing. Reflecting means collecting. But technically, you can implement it in very different ways. And the way I will focus on is this spaceborne platforms. Okay. Any other question? Are you okay with this concept? Okay. So this part of the course focuses on what happens here. Then we will move on to data processing. So what is electromagnetic radiation? It's a wave of changing electrical and changing magnetic field. Basically, fields are perpendicular. Yes, they're perpendicular to each other, and they propagate at the speed of light. We know that this is all governed. This is technically called a plane wave, and it is governed by the so-called Maxwell equations. Right, so any one of you who has a background in electromagnetism or physics can understand this. Luckily enough, when we do remote sensing, we don't need to come up with models, or we don't need to play with Maxwell equations. For most applications, we are happy modeling it with a energy packet or power. Maybe it's power traveling at the speed of light on a straight line, more or less straight, because obviously you have diffraction, deflection effects in the atmosphere, etc. But as a first approximation, we can say so, travels unchanged at the speed of light until it encounters an object, which generally is the observed object, interacts with the object and gets reflected with some possible way. This interaction involves changing the wave, and that's where the phenomenon that I mentioned noise. Now, a very important feature of the wave is its so-called wavelength, which is the physical distance between two maxima. And it's not a philosophical concept, it's a very practical concept because different wavelengths basically relate to very different interaction modalities with the target. So if you change the wavelength, you change the way of observing the object. And we have a perception of that ourselves with our own remote sensing devices, natural remote sensing devices, which are our own eyes. When you're attending this lecture, you're doing remote sensing in some way because I am illuminated by a source of electromagnetic radiation. This source throws electromagnetic radiation on myself. I am reflecting the radiation to your eyes, and your eyes are collecting information from it, right? So this is remote sensing. It's not the type of remote sensing that I'm talking about, but still you see the basic concept of remote sensing is there. You're leveraging reflected radiation to see what I am doing. Okay, great. You can do that at different wavelengths. Theoretically, we have from 0 to infinite, but practically we can only do this at a limited range of wavelengths. And we usually reason it, if we think of satellite-based remote sensing, we consider these ranges ultraviolet, less than 0.4 micron, but this is rarely used because it has a number of issues. Visible between 0.4 microns of wavelength and 0.7 microns, then infrared beyond 0.7 up to a few microns, and then you have the microwaves, which means, well, not split millimeter, but I would say low centimeters. Okay, and you may notice there's a big gap here between microns and millimeters or centimeters, whatever. And there's another gap here because it said smaller than 0.4, but then there's little space here. So basically, from 0 to 0.4 roughly doesn't work. From microns to millimeters doesn't work. And then up, okay, this is a gray area, but still we can see there's a significant gap here. Why is such gap there? Because of the atmosphere. When you operate an Earth observation satellite, you need to take into account that your way is not completely clear. You have a satellite here, you have the Earth down there, you have the sun up there, and the traveling waves have to go through the atmosphere twice, downbound and upbound, okay? And so the atmosphere may have a significant impact on them to the point that you can no longer use that radiation because it gets completely suppressed by the atmosphere. In this scheme, we have the so-called electromagnetic spectrum with all the possible wavelengths. And on the vertical axis, you have the behavior of the atmosphere expressed in terms of how much of the transiting radiation is absorbed. Whatever is absorbed doesn't get to the other side of the trip. So when you have the full extent of absorption, 100%, no radiation will ever be recorded by the satellite. And the atmosphere is quite peaky in this. You see, it basically removes all the radiation with wavelengths shorter than 0.4. Luckily for us, I could say, because this is harmful to the human body. But on the other hand, it's also not usable for doing remote sensing. So we can start doing remote sensing at the so-called visible range. Visible range is called visible because it's that small portion of the electromagnetic spectrum that we can perceive with our own eyes. When you're doing remote sensing of this lecture, your sensors are operating here in this narrow fraction of the spectrum. Then we have the so-called optical window, which is between a fraction of microns to some 12 or 14 microns, depending on the area. This is called the optical window. And then it goes blank again, and that's the reason for the gap that I showed you in the previous table. And then it opens up again when you roam around millimeters to centimeters. Doesn't work very well. Usually you don't operate your systems here. You start with centimeters. For example, with band X, 3 centimeters. Okay, it gets clearer, so you can operate confidently here. And then you have the so-called microwave window. This is the reason why historically 2 very different types of remote sensing were developed. One was the so-called optical remote sensing, and the other one was called microwave remote sensing, with very different features and very different observables. Okay, so if you want to observe a certain variable, generally there's one best field in which to play, because some variables are best seen in one field, some other variables are best seen in the other field. This links to the discussion we had earlier after the question of your routine. Okay, so as a very, very general and broad rule, if you want to learn something about the chemical composition of an object, if you want to identify the material that a certain object is made of, you usually look at this area. If you want to identify other parameters, such, for example, electrical conductivity, so if you want to tell metal from isolating matter, or you want to identify humidity, presence of water. If you want to identify density, then this is where you may want to look. Okay. And the 2 sets tend to be quite different from each other. That's the reason why we think of data fusion, in order to be able to get a more complete range of information items about the object that you're interested in. Okay.
Can you quote the applications of these 2
Sorry?
Applications of these 2 categories?
These are very broad. Generally, I can tell more than the applications. I can tell you the type of information that you can get from them. But frequently, every application picks up something from one or something from the other. Like, for example, if you think of agricultural applications, which I know best, agricultural applications, for example, use this part of the spectrum in order to source information about the health status of the plants. And from health status, you can see many different applications. Or you can use this part of the spectrum to derive information about soil humidity, about density of the plants, about the level of development of the limbs and branches, and things like that. From which you can then think of applications. Like, for example, precision agriculture uses mostly this because of the highest level of spatial resolution, but you can also use pieces of data from this because soil humidity is also relevant to precision agriculture. So it's generally a mix. There's no clear boundary between applications on using one or using the other type of data.
Difficulties we get when we are trying to fuse those 2 data.
Well, I already mentioned some of them earlier. I would say from there are practical difficulties, which is the fact that you have to buy or to purchase two sets of data, and you have to handle two data use licenses at a time instead of one. One is already a headache. If you have two, it's even worse. And that's not technical, but you still have to take that into account. From a practical standpoint, it's a fact that they generally, as I mentioned earlier, they generally don't come with exactly the same dates. So if time is critical for you, because you generally have multispectral satellite systems and microwave satellite systems. You don't generally have platforms carrying both. Even if they were carrying both, for technical reasons, multispectral component would not be easily observed in the same area as microwave component, because they work differently, they cannot look exactly in the same place. So I would say one big part of the difficulty in merging these two types of data relates with the fact that you don't have same time availability of data on the same area. Okay, so the concept is fascinating. Say, okay, I get information A from here, I get information B from here. Even better if I put them together. But then when I try to do that in practice, I realize it's more difficult than I thought initially. Okay. Then, if you're interested in more specific aspects, we can discuss that offline. Okay. So, when I say information collection, and especially the determination of the type of material which I am observing, one important concept to understand is that of the spectral reflectance. So this means like zooming into the concept of reflected radiation, which has recorded somehow the features of the observed object. What do I mean by has recorded the feature of the object? Well, a simple way of explaining it is like it's that of an energy balance. If I assume, it's not 100% true, but still acceptable as an approximation. If I assume that I'm dealing with a linear system, then every single wavelength, meaning every single frequency of the radiation which is landing on the observed object, can be treated independently. So because there's no pouring of energy across wavelengths. So at every wavelength, I have an energy balance between the energy which lands on the surface, and part of it is absorbed and part of it is reflected. Right? So since the energy conserves, whatever gets absorbed and translated to other forms of energy doesn't get reflected. But the energy which is absorbed depends on the chemical composition, depends on the resonating frequencies of the molecules which compose the target. That's the important point. When the radiation lands on a target, it's a wave of electromagnetic radiation. It acts on the electrical charges which are found in the molecules of this object. And the molecules of this object react in a typical way which is linked to its shape and distribution. So it's related with the chemical component that lie inside it and to their structure, how they are bound to each other. Meaning that some wavelengths will resonate easily, and so they will be absorbed by the structures, and others will not resonate and will be rejected. This is basically a zooming into this concept. Why do I get a reflection which is linked to what is found here? Because whatever lands there gets selectively absorbed. Different wavelengths will be absorbed to a different extent because I have different structures, different molecules, different atoms inside that structure. Does that make sense to you? When I operate the system in this area of the spectrum, I'm operating on frequencies which are comparable to resonances, to resonant frequencies of the molecules. That's why I observe this phenomenon, because these radiations may make the molecules to resonate. And depending on how the molecules are done, they will resonate at different frequencies and they will eat up different components of the radiation. So when I look at the reflected radiation, at the reflected components at the different wavelengths, I am somehow looking at the signature of that material. So the example that I usually mention to my student, it's like having a map of a key. See, this is a key. It's my home, by the way. And it's done in a specific way, and the lock recognizes it because it recognizes the shape. Okay? And so I can open my door because this is a recognizable shape. Other locks have different shapes. Okay, so my door will not recognize them and will not open. When you do optical remote sensing, multispectral remote sensing, you're somehow reading the key, the shape of the key that comes out from that specific target, and you can relate that to some known types of material. And so you can do a basic operation in remote sensing, which is called land cover classification. So because of this phenomenon, for example, vegetation will react in a certain way. One type of vegetation will react in a different way with respect to another type of vegetation. And both will generate a trend which is very different, for example, from bare soil or from urban land cover, etc., etc. And I call it land cover, but actually what I'm looking at is the chemical composition. I can recognize vegetation because its composition, its resonances, its molecular resonances are very different from those of bare soil because they are exposing very different types of material to the view of the satellite. Okay. And this leads us to another important point, to another important note which I want to make here. When you think of remotely sensed data, don't think of pictures. These are not pictures, okay? What you're doing when you acquire data from satellite is you are recording radiation power, radiated power. Some, but very few, some of that recorded data, this portion, but you're actually recording all of it, this portion can be used, but not necessarily is, can be used to build a human understandable figure of the observed area. That's what gives you the illusion that satellites take pictures. They're not taking pictures. They are recording incoming radiation. What is the difference? The difference can be seen here. practical difference is when you talk about the picture, you're talking about this amount of information. When you talk about multispectral acquisitions, you're talking about this amount of information. It's a lot more, of which you can only see a small fraction if you just look at the picture. Okay? So the picture is still important because, for example, all the computer vision, but maybe not all, but the most of the computer vision approaches to remotely sensitive data processing originated from this, from the fact that you can actually think of it as an image and you can process it as if it was an image. But again, it's not an image. It's a recording of incoming power which has a physical meaning, and you need to leverage the physical meaning if you really want to understand what is going on there. Okay? Naturally, you're welcome to look at the picture, but that's only really a small part of the story. Now, what time is
11:45.
Sorry?
11:45, right.
11:40.
We have, I think, 10 minutes break.
Yeah, we should have a break now, right?
I don't know.
The program says I have already gone beyond the program because this is it was supposed to end at 11:30. So I think if you agree, we can take maybe a short break now. I can discuss offline during the break with some of you if anyone has any question, and then we will resume in 10 minutes. Is it okay for you? Okay. So thank you, and see you in 10 minutes.
ठंड लग रही है? बोल रहे हैं